then how to write different things in this language of differential forms. Okay. Okay, consider this Hodge-Star operator in Minkowski space. So what was Minkowski space? So it's a collection of four vectors. 4 P, x1, x2, x3. Okay. P is something non-negative. Maybe it could be. So all these are real numbers. Huh? All these are real numbers. Okay. What would be the two forms in, for example, in Minkowski space? So that's what would be the collection of a space of two forms in Minkowski
Sir,
space?
span of dt wedge dx1.
So it's like all possible two, what do you call it? Wedge products. Okay. Interestingly, when you apply star, by the way, star operator is going to send you things from where to where?
0 form.
Not 0 form.
In this case, 1 form.
So what's the dimension of this? So it's a 4-dimensional. Okay, so what would be the dimension of this actually? So it would be 4 chose 2. So it must be something 6-dimensional like this. So that's a 6-dimensional exterior space. Okay? Because the dimension of Minkowski space itself is 4, and you are considering the two forms. So the dimension of this would be the span of at least 6 vectors. So we can apply star, I can treat the star as a map from this space to where?
4 minus 2, 2.
So 4 minus 2 would be 2 again. So it's going to be a kind of a division. Obviously you consider different indices, you get the different results.
So इसकी dimension 6
N
है
4 कैसे है?
तो 6 minus 2 होगा ना
So what is the dimension of your underlying manifold?
4
So it's a 4. So 4 minus 2 would be interestingly, I can consider, so what would be the possible products here? So what would be the basis of this vector? What would be the basis here? So the basis is going to be, okay, so you can have dt wedge dx1 and dt wedge dx2 and dt wedge dx3 and dx1 wedge dx2 and dx2 wedge dx3 and dx1 wedge dx3. Okay? These are only going to be the possible bases actually, otherwise the rest can be written as a combination of these. So this would be essentially the basis. Interestingly, when I apply, and you can verify it, okay, when I apply star on each of these, okay, it's going to do what? It's going to split this space into two basically subspaces. So in other words, what does this star is going to do? Basically, I can see this two exterior space on Minkowski space as a direct sum. As a direct sum of what? As a direct sum of plus, let me use a symbol, plus M13 and 2 minus, I'm going to define in a moment that what these are, M13 actually. So how many of you guys remember the direct sum? So if a vector space is a direct sum of, okay, two subspaces, okay, then what does it mean? That each vector V can be written as uniquely as a sum of A plus B, and
A intersection B is fine.
and the A intersection B is not 5, can't be 5, but it must have a 0 in between them.
Yes.
Okay. Now my claim is that I can see this Minkowski space as a direct sum of these two spaces. And what is this plus M1 3 space? Okay, an exterior space of two forms in Minkowski space. It is something that is spanned by these vectors. Okay, so it's like this is a span of dx, okay, dt wedge. I mean, if I wish, I can call it t as x naught, okay, for the sake of simplicity. Okay, so I have a dx naught x1, dx naught wedge dx2, and dx naught wedge dx3 actually. Okay, and this minus, okay, so it's like exterior space, okay, Minkowski that is spanned by
dx1
dx1 wedge
dx2
dx2 wedge dx2
wedge
and dx2 wedge dx3 and dx1 wedge
3.
dx3. Okay, yes. Now, why I am claiming that this subspace can be written as a direct sum of these two subspaces? The reason is this Hodge-Star operator. Let's apply Hodge-Star operator onto each of these. My claim is that if you apply, for example, the Hodge-Star operator on this expression, you're going to get one of these expressions. And for corresponding to this, you're going to get one of these, and corresponding to that, one of these actually. Okay? So here's the thing. So just treat this as an application, okay? What these things are doing. What would be star dx naught wedge dx1?
dx2
So it will be 1 over 4 minus 2 factorial. Okay? 1 over 4 minus 2 factorial. Epsilon 0, 1. So you have a no choice except having a 2, 3 here. Okay? And you're going to get what? dx2 wedge dx3. So you have this 1 over 2. Okay? Times what would be epsilon 0, 1, 2, 3? So that is even permutation actually. Okay? Because everything is fixed on its position. Okay? So you get a 1 here, and you get dx2 wedge dx3. Okay? No. I think we must have okay. So you're gonna have a K and L here. Okay? So you're gonna have a K and L here. It's fine. Yes. Because you're not only going to have a 2, 3, but you're also going to have 3, 2 actually. Okay? So it's not, so you can have a 2, 3 here, but you can also have a 3, 2 here. So if this would be the case, so if you have a 2, 3 here, okay? So then you get this plus, if you have R maybe minus, so what you're gonna get? If I have epsilon 3, 2 here, okay?
dx
Huh? So 1 over 2 epsilon 0 1, you get 2 3 and dx2 wedge dx3
Plus
Plus
1 by 2.
epsilon 0 1
3 2
3 2
dx3
and dx2 dx3 or dx3 wedge dx2. Okay, so you get this. So what did you get? What would be 0 1 2 3? Would that be minus 1 or
So minus
One.
2 3 is a single transposition.
so I have this kind of a transposition 0 1 2 3. Okay, so that's my transposition. So it's an even transposition. Huh? Okay, so it's an even transposition. So you're going to have a 1 here. So 1
dx2 dx3
wedge dx2 dx3 plus you're going to have a here minus 1. So two of them are fixed actually. So you're going to get transposition as 3 2 simply. Okay, so simply 3 2. So you're going to have a minus 1.
Again by
Minus
3 dx2 सही है सर
again लगाएंगे 80 symmetry.
क्या मतलब? अच्छा प्लस कर दे और dx2 wedge dx3 कर दे.
सही है
Okay, so what did you get?
2 times.
So you get 2 times of this and hence you get dx2 wedge dx3 actually. And so what does this show is that the star is mapping like this wedge product onto dx2 dx3. So as I claimed that each of this vector would be mapped onto one of the vectors here. So in other words, I can say that if I take a vector from the subspace that is spanned by these vectors, it would be mapped onto a vector that is spanned by, not a vector, but the better would be to call it a 2 form. Okay? So what the star is going to do is going to take a 2 form that is spanned by these vectors, these bases, wedge products, and is going to map them on the 2 form which is mapped by these wedge products actually. So in other words, kind of this star is splitting the space into the 2 parts, and you can do other way around as well. So you take the star, operate it on these any element or any what do you call a 2 form, okay, that is written in the terms of these bases, and you operate a star on it, you're gonna get a 2 form written in this subspace actually. So what essentially you can say is that somehow this star is telling you that Minkowski space must have 2 crucial parts, and which should have kind of only one thing in common, and that is 0. And this is true. I mean, if you have encountered some of what you call Minkowski space, you specify completely Minkowski space by a cone actually. A cone. Okay? In which you say that okay, that's my future, that's present, and that's past actually. Are you getting the point? So if I see mathematically, I can treat that as a subspace, okay, in the future, past, and with the origin in common with them. It's just kind of a direct sum. Okay? So you can treat that, you can see it mathematically that what the Minkowski space is really a kind of a direct sum of 2 of its subspaces. So now I'm trying to get into this light cone, but this has lots of interesting. Yes.
यहाँ पे notes की minus D.
There are typos. So check them out. Check your facts always. Okay. So we are doing calculation. It turns out that. Okay. Is it making sense? So let's move on. Divergence. that you can write, so it's like these are the two operations using which you can express any of these operations actually. Not only this but many other things as well. Okay. So in other words, so Sukkur, the gradient divergence can be put into a one single form. Not only not a one single form, but they can be expressed using this exterior derivative and Hodge-Star. Now how to express it? Let's do it. So what's gradient? I know that the gradient is this. Okay, del phi, classically. Where f is something like a scalar field, a smooth scalar field from R3 to Rn. So what would be the expression for the gradient using one of these algorithms? Okay. So take the exterior derivative of this scalar field or zero form f. Okay, so take the exterior derivative of the zero form f. So what are you going to get on the other side? So we're going to get partial f by partial xi.
T of x.
So you're going to get this one form f. Okay. So this one form is what? This form is the gradient of f dot product with dx. Okay. This is just a specification of coordinates. So in other words, the gradient of f, when written in the language of exterior calculus, is basically the exterior derivative of this zero form. It's this exterior derivative of this, this scalar field.
Zero form.
Okay? Exterior derivative of a zero form or a scalar field. Alright? So that's a what you call differential form representation of the gradient. Let's take a one form. Okay. Okay. The next is how to express del cross A. You can express curl in this language. So take a one form with the so one form of this AI and dxi, and compute the exterior derivative of this. So d alpha. So the d alpha is going to be partial ai by partial xj and dxj wedge dxi. Okay. And we discussed it yesterday that if I am computing the exterior derivative of a one form, I can rewrite this expression as 1/2 partial ai by xj minus partial aj by partial xi and dxj wedge dxi. Okay, dxi wedge dxj. I can put it in this manner. All right. So how we get from here to here? Refer to yesterday's lecture. Or you can basically expand it. So you do 1 1 and 1 2 and 1 3 and 2 1 and 2 2 and 2 3 and 3 1 and 3 2 and 3 3. You're gonna see that 1 1 would be 0. 1 2 and 2 1 can be combined, and 2 1 1 3 and 2 3 can be combined, and so on and so forth. So you're gonna get such kind of an expression. Okay. Now let's apply star on this exterior derivative. When you're gonna apply the star on this exterior derivative, so you have this d alpha. Let's apply star on this exterior derivative. So you have to apply star here. Okay? You have to apply a star here. And then this would be what? Okay, so this would be what?
We have recently done.
This would, huh?
अभी अभी हमें वो determinant
We just wrote it basically. We just wrote it. So I can write this as what? Del cross A dot dx. Del cross A dot ds. Why? Think about it. What we just said. So the star of alpha wedge beta is what?
ith component of it.
Okay. So you take the A cross B, so the wedge of the ith component and write a dx size.
Which is
So how can I write it? So I can write this as the dot product. So I can see this as a dot product. So I can do the precisely same thing. Okay. So I can see this thing as del cross A, taking the dot product with dx. So in other words, what would be the curve using the differential form notation? So this is the differential form notation for the curve vector. Okay, that star d alpha. In other words, take a one form, okay, and apply d on it. Okay. Here's the one interesting thing. Okay, obviously this is true in R3. This is true in R3. But even if you are in Rn, okay, you can't write it. You can't write it because you don't have a curve in higher dimensions. But I can treat this quantity as an analog of a curve in higher dimensions actually. Because this is curve in 3 dimensions, it's meeting with our intuition, star d alpha, that's curve in 3 dimensions. Okay, I know that this notion is restricted in 3 dimensions, but not this notion, so above notion. So I can treat, okay, this is star d alpha as a kind of an abstract curve in higher dimension. Because we are extending this notion actually. And you can argue precisely same thing for here actually. Okay. Okay, the gradient exists in higher dimensions as well. So it's not something too much interesting, but this is interesting. Alright. How can I write divergence? How can I write divergence? So for divergence, I have 2 ways to write it. So for divergence, I have 2 ways to. I'm not just doing it to do the calculation for yourself, but I'm just mentioning it. How can I do the divergence? Imagine you have a 2 form. Okay, like a b1, say dx2 dx3 plus b2 dx3 wedge dx1 and plus b3
dx1 dx2
dx1 wedge dx2, okay, something like that, and compute the exterior derivative of it. Okay, compute the exterior derivative of it. So if you get the exterior derivative of it, you're going to get something interesting. You're going to get this. Okay, I'm just writing the result. Partial b1 by partial x1, partial b2 by partial x2 plus partial b3 by partial x3, and wedge product. Obviously, you're going to get a 3 form. The exterior derivative is going to send this 2 form into the 3 form. So you're going to get dx1 wedge, dx2 wedge,
dx3.
okay?
Yeah.
Then if I'm applying d, the exterior derivative onto a 2 form, Okay, so it seems a pretty abstract notion. It has nothing to do with the real world, but now I can interpret it.
Divergence.
That it's the divergence of B in a small unit of volume. Isn't it? So now I can interpret the exterior derivative, okay, of a two form as the divergence of B, the vector field that is, formed by the components in a small unit of volume.
Integral of cross divergence.
And if I have a one form, beta I dxi, okay, you can actually show that take this alpha, operate star on it, okay, and then compute. So when I'm operating a star on it, is going to send it where? So maybe if you are in, for example, R3,
तो 2 में जाएगा.
so it's going to give us the two forms, huh? So that would be a two form. And now I'm operating D on it.
3 4.
You're going to get a three form, okay? And now again operate star on it.
0 में चला जाएगा.
You're going to get a zero form out. And that zero form is the divergence. So show it. Okay. And that zero form is divergence. So alpha is one form, star is throwing it, making it two form. Okay, you operate D on it, it's going to make it three form. Okay, and you have a three form and you are inputting it into a star operator. So it's going to throw it into what? Okay, it's like a 3 minus 3, so it's a zero form. And that zero form would be the divergence of the BF. Okay, so that's an expression for the divergence. That's an expression for a divergence in a volume element. Okay. So verify these. That's an important thing. Can I write Laplacian, Laplace operator, but in this language actually? Okay. By the way, what is the nature of this quantity? Is it a vector field, a scalar field, what? It's a zero form.
Scalar field is 0 form.
Okay, it's a scalar. So take F. Okay. Compute the exterior derivative. So you get a one form. Compute the star. What you're going to get? You get a two form. Compute exterior derivative again. You get a three form. And again a star. You can guess it actually. So you get
0.
what? You're going to get this del square F. Check it. Okay? The same thing again. Okay, by del square F, obviously I mean the divergence of the gradient. Okay, so divergence of the gradient. Okay. So you see, this D and star is doing amazing things. So it's kind of combining all these different notions that you have previously, which have kind of no relationship with each other. Now you can just express them using D and star. Obviously they have a relationship with each other, but so using star and D, you can kind of unify them. So it's kind of a unification, that's a unification theorem for them. Okay? But not only unifying them, but generalizing them. Think about it. Okay? This expression obviously exists in R3. Okay? In R3 it's equal to this, but in Rn it will be something else. Okay? So in other words, this Laplacian, okay, so obviously like this is divergence in R3, okay, this is divergence in R3. But so if you are in higher dimension, you can treat this quantity as divergence entity in higher dimensions. This will be very useful, sir.